Yeah, hello my viewers. This is the continuation of variable separable. Today we are going to talk about equations reducible to homogeneous form. Now, there are various ways of solving variable separable. So this one is a little bit different from the one I solved in the last class. Now, today we are going to look at the equation in a reducible to homogeneous form. Now, we have two different cases of this form. One, a case whereby the gradient is not equal to the other gradient, which is perpendicular. In that case, we represent our small s with what? With an increase in length, and our y with an increase in y. So in that case, our ds is equal to the x, the capital S, while our dy is the capital Y. So meaning that our differentiation of small s is the same thing as when you differentiate the bigger s. Likewise, small y is the same thing as the big Y. So they are what? They are interchangeable. Now, this case is perpendicular. Perpendicular in the sense that the midpoints are not equal. So if the midpoints are not equal, we follow this procedure. Yeah, as I said earlier, I said these are the procedure of solving differential equation into a reducible homogeneous form. In case 1, the two straight line will be perpendicular. So if the two straight lines are perpendicular, these are the procedure of solving them. Now, I've explained this, that our change in small s is the same thing as change in big S, and our small in change in y is the same thing as what? Change in big Y. Now, the next step is to make this value here to be equal to 0. We solve for the value of h and k. We are going to rewrite the ordinary differential equation, then solve the homogeneous differential equation. So for case 1, it must be perpendicular. If it is perpendicular, this procedure will be followed. Now, let's go to case 2. In the case of case 2, our gradients, which is m1 and m2, are parallel. When I say they are parallel, it implies that the gradients are the same. And after that, we differentiate the equation by assuming the value of ax plus by to be equal to z. Then we solve the resulting homogeneous differential equation. Now, let's go to the question itself. How do we solve the question in form of perpendicular and in form of parallel? Now, let's look at this example. Look at this example 1. We are given the y ds to be equal to 2x plus 9y minus 20, 6x plus 2y minus 10. Now, let's look at this calmly. This is our numerator and this is our denominator. Now, let's look at this. In the case of the first one here, we have 2x plus 9y minus 20 equals 0. For instance, let's find our midpoint here, for you to know if you are using case 1 or case 2. Now, when 2x plus 9y minus 20 equals 0, 9y will be equal to 20, or let me put it like this. That will be minus 2x plus 20. We divide through by 9. Then our y will be equal to minus 2 all over 9x plus 20 all over y. So, for the numerator, our m, let me call it m1, will be equal to what? Minus 2 all over 9. So let's solve the denominator. If you look at our denominator, my 2y will be equal to minus 6x plus 10. So when you divide 4 by 2, our y will be equal to minus 3x plus 5. So here, our m2 will be equal to minus 3. So m1 is not the same thing as what? m2. So in that case, this differential equation is perpendicular. So we are going to use case 1 to solve this problem. Now, let's follow the procedure. I'm sure you understand the explanation. So we are given this differential equation. So you can agree with me now that it is perpendicular. Now, let's go to the next step. Looking at the procedure here, now we assume our small x will be equal to x plus h. So we have our what? S to be equal to capital S plus h, and our y to be equal to what? Y plus k. Meaning, anywhere you see the small s in the straight line, you substitute this value. So let's do that. Don't forget that our change in y and change in s as well will change. To the y, the x, to be equal to 2. Now, instead of writing the small s, we write our capital S plus h plus 9 y plus k. Let me clean this. Minus 20 all over 6 x plus h plus 2 y plus k minus 10. Then we expand. So we have 2x plus 2h plus 9y plus 9k minus 20 all over 6x plus 6h plus 2y plus 2k minus 10. So we have this. Then the next step will give us, now let's bring all these values together. Don't forget we said our AH, BK plus the constant will be equal to 0. So we make sure we rewrite our equation in such a way that we are going to achieve this AH, BK, and C. H, K, and C. So which implies that this, and this will be both together. So we have our 2x here plus 9y plus 2h plus 9k minus 20 all over 6x plus 2y plus 6h plus 2k minus 10. Then look at this. Let me bring this up here for clarity. Then our 2h plus 9k minus 20 will be equal to 0. And our 6h plus 2k minus 10 will be equal to 0. Now we have these two simultaneous equations. Now how do we go about that? So let's solve this simultaneous equation. Now from h, let me call this equation 1 and let me call this equation 2. So we need to get the value of our h and k. So from 2, we have our 6h plus 2k to be equal to 10. 6h plus 2k to be equals to what? To be equals to 10. Now let's make our 2k the subject of the formula. So we have 2k to be equal to what? 10 minus 6h. My k will be equal to 5 minus 3h. So this is the value of k. Let me call this equation what? Equation Roman figure 3. So if k equals 5 minus 3h, then we can substitute our k in equation 1. So let's solve for k in equation 1. So in equation 1, this is our equation 1. So anywhere you see k, you put this value of 5 minus 3h. So that becomes 2h plus 9, 5 minus 3h minus 20 equals 0. So this will be 2h plus 9 times 5 is 45. 9 times 3 is what? 27h to be equal to 20. So we have 2h minus 27h. That will give us minus 25h to be equal to 20 minus 45. So 25h will be equal to what? Minus 25. So my h will be equal to 1. So our h is 1. My h is 1. So if h is 1, you can substitute for our h in equation 3. So equation 3 now, look at this very well. Equation 3, Roman figure 3, becomes k to be equal to 5 minus 3 bracket 1. And that will give us k to be equal to what? 3 times 1 is 3. 5 minus 3 is 2. Our k is 2. So by solving this simultaneous equation, we are able to get our k to be equal to 2 and our h to be equal to 1. So our question continues. Don't forget that we assume the whole of this to be equal to 0. We assume the whole of this denominator as well to be equal to 0. Then we can solve this resulting homogeneous differential equation. Now, let me solve this differential equation. So we have our dy ds to be equal to 2x plus 2y all over 6x plus 2y. As we always do, we assume our y to be equal to vx. Let me do it somewhere here. Let our y to be equal to vx. So if our y is vx, we can easily get our dy dx to be equal to what? V plus x dv ds. So if you watch the last video, you understand how I use the product rule to get this. Now, how do we interpret this? Our dy dx is the whole of this, which implies that instead of writing the y ds here, we can easily write the whole of this value. And instead of writing y in the equation, we can write vx. Now, our dy ds now turns to v plus x dv dx to be equal to 2x plus 9 vx all over 6x plus 2 vx. Now, from this, x is common. So we have our x bracket 2 plus 9v all over, this becomes what? X 6 plus 2v. So x will cancel s. So we are left with v plus x dv dx to be equal to 2 plus 9v all over 6 plus 2v. Now, by bringing this v to the right hand side, and because it's crossing an equal to sign, we have x dv dx to be equal to 2 plus 9v all over 6 plus 2v minus v. Now we have that. Then we need to solve this. You find the LCM of this, multiply all the sides, we are going to obtain our value of 2 plus 9v minus bracket 6v minus v square and so on. So let's solve this. We have x, the v, the x to be equal to, let's find the LCM of this. The LCM is what? 6 plus 2v. So when you have this, you have 2 plus 9v minus this, we multiply the whole of this, then we have v, we have 6v minus plus whether 2v squared. So at the end of the day, the whole of this will give us 2 plus 9v minus 6v minus 2v squared all over 6 plus 2v. Don't forget we still have our x, the v, the x. Now let's simplify this. What are we going to obtain after simplifying? We are going to obtain a quadratic equation. A quadratic equation of minus 2v squared plus 3v plus 2 all over 6 plus 2v x the x. So we have a quadratic equation of minus 2v squared plus 3v plus 2 all over 6 plus 2v. Now, how do we solve that? At the end of the day, we are going to obtain a simplified quadratic equation where we have this will be, so from here, if you look at this differential equation very well, we now have homogeneous equation where we have v and the value of x alone. So by now it can be easily separated. So here, if you want to separate this, we have 6 plus 2v all over minus 2v squared plus 3v plus 2 integral of the v to be equal to what? Integral of the x all over x. So we have this. So let's change all of this to a simplified a solution to our quadratic equation. I'm sure you can also solve quadratic equation. So we have 2v plus 1 bracket 2 minus v. Two v plus 1. Let me solve the quadratic equation so we are going to understand it very well. Let's solve the quadratic equation so you understand how we arrive at our solution. Now look at this. 2v squared. Then we can easily solve this. Then we have 4v squared. We have 4v v. Because this is plus 3, so this will be plus and this will be minus. After substituting this value, we are going to obtain an integral of 6 plus 2v all over 2v plus 1 bracket 2v plus 1 bracket 2 minus v. 2 minus v, the v, to be equal to the integral of the x over x. So for this quadratic equation, you multiply the first and the last term together, then we are going to obtain minus 4v squared. And after getting 4v squared, get a value that when you multiply together will give you the resulting value, and the addition will give you the middle term. So that's how we obtain this. If we expand this, we are going to get the same value. Now we have this. How do we integrate this value? This is very straightforward. The integral of 1 over x is ln x plus a constant. But in this case, there is no way we can integrate this. We can only integrate this by using a partial fraction. So we solve this value inside this integral by partial fraction. And after solving by partial fraction, then we can easily collect like terms and solve the resulting question. Now let's solve this partial fraction. I'm sorry, I will need to rub this off. Now let's solve this partial fraction. We have the integral of 6 plus 2v over 2v plus 1, and we have 2 minus v dv. Now, I'm not looking at the integral now. Let's solve this by partial fraction. We assume a over 2v plus 1 plus b all over 2 minus v. So this implies that we have 6 plus 2v to be equal to a 2 minus v plus b 2v plus 1. So this is how to solve partial fraction. I hope you know how to do this. Now let us put v to be equal to 2. We assume v to be equal to 2. If v is 2, the whole of this will be 0. I mean, if you put 2 minus 2 here, 2 minus 2 will be 0, and the whole of this will cancel out. Right? So if the whole of this cancel out, we are left with 6 plus, put 2 here, that will be 4. So the whole of this will be 10. Will be equal to, put 2 here, that will be 4. 4 plus 1, 5. We have 5b. So at the end of the day, our b will be equal to 2. Now, we've assumed v to be equal to 2. The next thing is to assume v to be equal to minus 1 over 2. How do we get that? You assume the whole of this here, 2v plus 1, to be equal to 0. So our 2v will be equal to minus 1. V will be equal to minus 1 all over 2. So that is where we got our minus 1 over 2 from. And we got our 2 here. Because we have minus 2v to be equal to 0, v will be equal to 0. V will be equal to 2, rather. So that is where we got this from. So we've assumed v to be equal to 2. Let us assume v, or let v to be equal to minus half. It's not an assumption. We let v to be equal to minus 2, and we let v to be equal to 2 here. So if we do that, here we are going to have 6 plus 2 minus half to be equal to a 2 minus half. So the whole of this will be 0. So minus 5 minus half will give us what? Addition. So we have 6. This will cancel out. We have 6 minus 1. That will be 5. To be equal to here. If you have here, this one will give us 10 as well. So let's look at this. A will be equal to what? 2 plus half. This will be 2 plus half. At the end of the day, we have 5 all over 2a, which will give us a to be equal to 2. So, after solving this partial fraction, I was able to get the value of our a and b. Our a is equals to 2, and our b is also equals to 2. So, we are resolving this in partial fraction in order to simplify the integral. So, after solving this, it will now be easier for us to solve this integration. Now, let's look at it together. So, we have this. So, the whole integral here has been denoted by this. Then we have our a to be 2. And what? B to be 2. So our integral now will now be 2 all over 2v plus 1 plus 2 all over what? 2 minus v. All dv. Don't forget, we still have integral of the x all over x. Now we can easily integrate this. So let us integrate this. This is now, we can easily separate this down. According to the rule of integration, integration states that if we have ax plus bx in integration, all dx is the same thing as integral of ax dx plus integral bx dx. So it's the same thing. So we need to separate this integral. And how do we go about that? On solving that, we have this to be the integral of 2 all over 2v plus 1 plus integral 2 all over 2 minus v. Now, this is a constant, this is a constant. So this can be in form of 2 integral of 1 all over 2v plus 1 plus 2 integral of 1 all over 2 minus v. Now, look at this. How do we go about this integral, dv? I know the answer, but I need to simplify it in such a way that you guys will understand what I'm doing. Now, let u, this is dv, let u be equal to 2v plus 1. Definitely our du will now be what? V plus 1. Our dv will be, we differentiate it, our v will be what? Our du rather will be 2 dv. So if our du is 2 dv and we have dv here, so we can have our du all over 2 to be equal to dv. So instead of writing dv in this integral, we can write du all over 2. So I hope you are getting what I'm saying. Du all over 2. So the whole of this integral here will be 2 integral all over what? 1 all over u dot du, du all over what? All over 2. So it's an instance. So plus 2 brackets 1 all over 2 minus v dv. Now this is a constant. The constant is in form of a fraction, 1 all over 2. So this will cancel out this. We are left with 1 all over u. And 1 all over u is ln u. Plus, now you can easily differentiate this. There is a rule, if you differentiate the denominator, this is a constant, this will be 0, and this will be what? Minus 1. So because minus 1 is the same thing as the value we have at the numerator, so this will change to minus 2 ln 2 minus v. So let me rewrite the whole of that. I hope you understand this. What I do here is to integrate this. I integrated this. So for this, we got ln u. And for this, we got 2 ln 2 minus v. So I want to write it in order. So after integrating this, we have ln u. And our u, if you check what we did, we assume u to be the whole of this. So this will be ln 2v plus 1 minus 2 ln 2 minus v. That will be equal to, if you integrate this as well, we have ln what? Ln x plus a constant c. So that is our value. But we need to simplify this further. And how do we simplify? So if you look at that very well, the whole of this, from the rule of logarithm, so these two will come as a power. So we have ln, let me put it, all over what? 2v plus 1 divided by 2 minus v all squared to be equal to ln x. xc. So this will cancel out. Then we are left with 2v plus 1 all over 2 minus v all squared to be equal to xc. Now, we need to make one or two substitutions. Initially, from the beginning, we assume y to be equal to vx. Now, we still have v in the question. So our v now can be written as what? Y all over x. Our v is 1 all over x. And at the same time, we assume our capital X here. So v will be equal to y all over x. V is y all over x. So anywhere we see v, we make our substitution. let's substitute for v. So we now have 2v plus 1 all over 2 minus v all squared to be equal to xc. Now our v is what? Y all over x. So this will be 2 bracket y all over x plus 1 all over 2 minus y all over x all squared to be equal to xc. At the same time, don't forget that we assume initially, if you check what we've been doing, our small x to be equal to x plus 1 and our small y to be equal to y plus 2. Don't forget, if you look at this equation very well, we assume we solve the resulting equation where we get our k to be equal to 1 and our h to be equal to 2. So we have this. And don't forget that what we have here is capital Y and capital S. So at the end of the day, our small s will be x minus 1 from these two. Small x minus 1 to be equal to capital S. And our small y will be y minus 2 to be equal to capital Y. Then instead of writing this big Y, we write it in form of y minus 2. Instead of writing s, we write it in form of small x minus 1. So this will give us 2 to open a bracket y minus 2 all over s minus 1 plus 1 all over 2 minus y minus 2 all over s minus 1 all squared to be equal to xc. No, capital X as well. So this will be x minus 1 dot c. Now we can easily expand. When you expand this, then we get our final answer. I believe we can easily expand this. Just multiply this by the numerator. That will give us 2y minus 4 all over x minus 1 plus 1. And we expand this by multiplying this twice. And at the end of the day, we are going to get our value to be x plus 2y minus 5 all over y minus 2x all squared to be equal to c. So this is our final answer. After expanding this, we are able to get this. Thank you. For clarity, I want to explain something based on what I've done earlier. If you look at this very well from the beginning, we have 2 minus v all bracket and square. So if you come down here, the square covers both the 2 and the y all over x. The same thing goes to this form. So the square covers this and this. So after factorization, then we obtain the final answer. So that is just the basic thing I want to explain here. Now, let's continue with the second case. The first question I solved a situation whereby the midpoint, the gradient m1 is not the same thing as what? M2. Now, let's look at this. This is a case where m1 is equal to m2. And I'm sure you can easily do that. Look at this equation we have here. We have 2x. Let me just do it directly. So this is y to be equal to what? Minus 2x minus 1. So our m1 here equals minus 2. Now for the second one, we have 4x plus 2y equals 1. Or let me do it like this. Minus 1 equals 0. So our 2y here will be equal to minus 4x minus 2y plus 1. By dividing all the sides by 2. Minus 1. If you divide all by 2, at the end of the day, our y will be equal to minus 2x minus, this should be minus 4x plus 1. Yes. So plus 1 all over 2. So our M2 here is minus 2. So M1 is minus 2 and M2 is minus 2. So in this case, we are going to use the second case. We use the second case to solve the problem. Now, a case whereby the M1 equals M2 is a parallel line. So if you have this situation, it is easier to solve compared to the a case whereby the gradients are not equal. Now, how do we solve this problem? Now, solving this, we have the whole of this differential equation to be equal to 0. Now, let us write it in a form where we can easily solve the problem. And how do we go about that? Here, I can easily write my dy ds to be equal to minus 2x plus y plus 1 all over 4x plus 2y minus 1. Now, we said the gradient is the same. Now, if you look at this and this, our dy ds will be equal to here, we have 2x plus y plus 1. Why here? 2 is common to this and this. So we can easily rewrite this as 2x plus y 2x plus y minus 1. So the next step is to let z be equal to 2x plus y. So anywhere you see 2x plus y, we can substitute the value of z. Now, if z equals to x plus y, so let's differentiate. If we differentiate this, we have our dz over the s to be equal to, so if you differentiate this, you have what? 2 plus the y ds. So let me call this equation 1. So the z over the s equals 2 plus the y ds. So we can easily make the y ds the subject of the formula. So we obtain our dy ds to be equal to the z ds minus 2. Let me call this equation 2. I hope you understand how I got this. I only make my dy ds to be the subject of the formula. So this comes to the left hand side. So we have the z ds minus 2. Now, having said that, we go back to our equation 1. No, let me call this equation 1. Let me call this 2. And let me call this equation 3. So we substitute equation 2 and equation 3 in 1. So meaning these 2 and equation 3 we substitute in this equation. So instead of writing the y ds, we write the z over the s minus 2 to be equal to, we have a negative sign here. So 2s plus y is to be z. So we have z plus 1 all over 2z minus 1. We have 2z minus 1. So look at this very well. In equation 1, we have 2s plus y. But we've assumed that z equals 2x plus y. So instead of writing our 2x plus y, we write z. So that's where we obtain z plus 1 form. The whole of this is z and plus 1. That's what we have there. And this, we have 2s plus y. We have 2 outside the bracket. So this is 2z minus 1. And our dy ds is the same thing as writing the z dx minus 2. So this is another way to solve a situation whereby the line is parallel. The line is parallel because the gradient m1 and m2 is equal. That means the gradient of m1 here, this, and the gradient of this is the same thing. So that's why we are using this method. It is different from the first method, which is perpendicular. So in this case, all you need to do is to assume the common value to be equal to z, differentiate them, and substitute back in the equation. So having said that, we have this. Now, for simplification, this is to be equal to, we can easily expand this, and this will give us what? This will give us, we can rewrite this to be 1 minus z minus 1. Yes, we can write this as minus z minus 1 all over 2z minus 1. So bringing these two to the right hand side, it will be what? Plus 2 all over 1. So let's find our LCM. This and this is 1. Multiply that by the numerator. You have minus z minus 1. Plus, use these two to multiply this. You have 2z minus 1. So we see how our dz, the x, and our dz, the x, here, will be equal to minus z minus 1 plus 4z. Let me put this sign as minus z to differentiate this from 2, and my z in this form, just to differentiate it from 2. So we have this by expanding minus z minus 1 plus 4z plus times minus is minus. We have minus 2 all over 2z minus 1. So this will give us, we have minus z here and we have plus 4z. So that will be 3z. Minus 1 minus 2 is minus 3 all over 2z minus 1. All is the z all over the s. So we have our dz, the s, to be equal to 3 bracket z minus 1 all over 2z minus 1. The reason why I wrote that is because if you look at this, 3 is common to both sides, then we are left with what? Z minus 1 all over 2z minus 1. So we have 3z minus 1, 2z minus 1. Now, if you look at this, it is now easy to separate the variables because we are left with just one variable, which is z, and another variable, s. So we can easily what? We can easily separate the variables. How do we go about that? So z will go to z and s will go to s. In that case, we are going to have 2z minus 1 all over 3 bracket z minus 1 all the what? The z integral to be equal to the integral of the s all over s. Now, so the next thing for us is to what? Integrate this and integrate this. Now, how do we go about this? If you look at this integral very well, our z, we have to do it in such a way that z, this cannot cancel out this directly. Do you get what I'm saying? So we are going to write this in such a way that it will be very easy to what? To integrate. How do we go about that? It's very straightforward. All we need to do is, initially we have 3 here. So let me simplify it in order. So this is 1 all over 3. We brought this 3 outside the integral sign. And we are left with 2z minus 1 all over z minus 1 dz. equals to this. Don't forget we still have this here. Now, how do we solve this? If you look at the numerator can be simplified in such a way that the denominator z minus 1 can easily cancel it out. How do we go about that? So what we have here is this can be written as 1 all over 3 integral of 2 bracket z minus 1 plus 1 all over z minus 1 z equals the s all over s. Now, let me explain this. Now, if you look at this integral sign, there is no way we can integrate this. You can't cancel z1, z minus 1, z minus 1 because they are not separate entity. So, I look at the numerator. I was like, look at this. If I introduce 2 and 1, if we expand this, 2 times z will give you 2z. 2 times z will give you 2z. 2 times 1 will give you minus 2. And we have plus 1 there. So if you look at this very well, at the end of the day, we have 2z minus 2 plus 1 is minus 1. You can see 2z minus 1 that we have here, 2z minus 1 that we have here is still the same thing as writing it in this form. 2 bracket z minus 1 plus 1, the z all over z minus 1. So we can easily integrate this. Now we have 1 all over 3 integral of 2 bracket z minus 1 plus 1 all over z minus 1 equals integral of the s all over s. Now, you remember in our elementary mathematics, if you have a plus c to be equal to b, how do you simplify this? This can be written in this form, a all over b plus c all over b. If you have something like this, it's still the same thing as this. So we are going to use this procedure to solve the integral. So this can easily be written as 2 bracket z minus 1 divided by z minus 1 all the z. I'm writing this in order to differentiate z from 2 plus this 1 over 3 covers this and this. So we still have 1 all over 3 integral of 1 all over z minus 1 all the z to be equal to integral of the s all over s. Now, this can easily cancel out this. So we are left with 1 all over 3 integral of 2 dz plus 1 all over 3 integral 1 all over z minus 1 dz to be equal to integral of the s all over s. So this is a constant. 2 will come out of the integral. We are left with 2 all over 3 all z plus this 1 all over 3. 1 divided by z minus 1. If you integrate this, if you integrate z, we have 1. If you integrate 1, you have 0. So because the integral at the denominator is the same thing as what you have at the numerator, then that will give us 1 all over 3 ln z minus 1 to be equal to what? Ln x plus c. So this is what we are going to have in respect to the value we are giving. So all we need to do now is to make our substitution. Initially, we assume z here in equation 2 to be equal to 2x plus y. So anywhere we see z, we put what? 2x plus y. So here will be 2 all over 3 to be equal to 2x plus y plus 1 all over 3 ln 2x plus y minus 1 to be equal to ln our normal x plus c. So using the rule of logarithm, we can easily solve this. Bring this 1/3 up there, then we combine them together. So 2 bracket 2x plus y plus ln 2x plus y minus 1 equals 3x plus c. So this will be our final answer. So our final answer is 2 brackets. And how do you get over that? Just look at this. The reason why the value is like that is we have 2/3 here, we have 1/3 here, and we just have ln x here, right? So, but we have 3 here, 3 here, and 3 here. So we can multiply all the sides by 3. You multiply all the sides by 3. So if you multiply this one by 3, 2 will cancel out 3. You'll be left with 2. If you multiply this one by 3, you'll be left with ln 2x plus y. And we have what? 3x plus c here. So this is what we have. So our final answer is 2 bracket 2x plus y plus ln x plus y minus 1 equals 3x plus c. So by now, you should be able to solve any problem that is related to variable separable using the reducible homogeneous form by determining the line if it's perpendicular. And when the line is parallel, you should be able to solve problem related to variable separable. Thank you for listening to my lecture. In the next class, we are going to solve linear and Bernoulli equation. Thank you.